In the previous lecture we were working out some problems on converging diverging nozzle and we will continue with that in this lecture. So, the problem that we are going to solve now is as follows. A converging diverging nozzle is designed to expand air from a chamber in which P0 is 800 kilopascal, T0 is 40 degrees centigrade to give M is equal to 2.7 at the exit. Area of the throat is 0.08 meter square. So, the questions are as follows. Number 1, what is the area at the exit? What is the design mass flow rate, that means the maximum mass flow rate that you get? What is the lowest back pressure for which there is subsonic flow throughout the nozzle? What is the design back pressure? So, I will write all the questions here and then because of interest of space in the board I have to erase the question part, and when we will be solving the problem we will get back into the question part one by one. What is the design back pressure? This is question number 4. Number 5, what is the back pressure for which normal shock will be there at the exit plane? what is the back pressure rather back pressure range for which there is no shock inside the nozzle. What is the range of back pressure for which there will be oblique shock at the exit? And finally, what is the range of back pressure for which there will be oblique expansion wave at the exit? Okay. So, this is a very comprehensive problem. It deals with different back pressure conditions for which different Mach number conditions occur at the exit. That is the whole essence of this problem. So, let me make a schematic of this problem and then I will erase most of the parts. I hope you have copied the problem by that time and then we will solve the problem one part after the other. So, you have a converging diverging nozzle. So, let me write P0 800 kilopascal, T0 40 degree centigrade, M design, I will write it somewhere, according to our theoretical description this is M for the point back pressure D, capital D, which is 2.7, I will draw this, and area of the throat is 0.08 meter square. Remember that area of the throat is not always A star, area of the throat is equal to A star when the sonic condition exists at the throat. So, one should not confuse area of the throat with A star, but there is a condition when area of the throat is same as A star, and that is the condition where the sonic condition itself exists, and if it exists we know it will exist at the throat. So, we will work out different parts of this problem. I have the question in my notes, so I will look into the questions and start solving one by one. So, the first question is, what is AE? We know a relationship between A by A star as a function of Mach number, right. So, AE by AE star, so this is, when can you use this relationship? This is isentropic relationship, right, no shock. So, if the design condition exists at the exist, that means you do not have a shock, right. So, when you have the design condition at the exit, you can use this with AE is that is what you want to obtain, AE is what you want to obtain. What will be A star? A star in that case, when the design condition exists, the critical condition is at the throat where the Mach number is 1, then one solution goes where the pressure increases and the Mach number decreases, and another solution goes where the pressure decreases and the Mach number increases. So, A by A star is a function of ME, where ME is MD, which is 2.7, right, and A star is A of the throat. So, from here you will get what is AE. So, AE is 0.255 meter square. Next part of the question, what is the mass flow rate under design condition? This is m dot star, right. So, rho star, A star, U star. So, you have now, how do you calculate rho star and U star? So, you can write, so you have P by rho is equal to RT, right. So, rho is equal to P by RT. So, P star by RT star, then A star, U star, U is equal to what? The Mach number times root over gamma RT. Star condition means Mach number equal to 1. So, this is square root of how do you get T star? You know the formula for T0 by T. So, T0 by T is 1 plus gamma minus 1 by 2 m square, right. So, T0 by T star is 1 plus gamma minus 1 by 2 into m star square, m star is 1. T0 is given, so from here you will get what is T star, and P0 by P is T0 by T to the power gamma by gamma minus 1. So, P0 by P star is T0 by T star to the power gamma by gamma minus 1. This will give you what is P star. You can remember that we solved one such problem in the context of converging nozzle, and the philosophy does not change because the maximum mass flow rate is guided by the throat condition if there is sonic condition at the throat. So, this if you substitute all these, this will be 146 kg per second. For the subsequent parts of the problem, let us recall the various pressure profiles P by P naught as a function of x, So, you have one typical case, maybe two typical cases we had shown as A and B, then this is C. So, this is D. Well, so then the next question, what is the design back pressure for which there is only subsonic flow throughout the nozzle? Okay. So, question is what is the pressure at this point C? So, you have A by A star as a function of Mach number, right. So, when you have A by A star as a function of Mach number, your question is as follows: which Mach number will you choose here? So, for D it is supersonic, for C it is subsonic. So, AE by A star, which is area of the throat, you will get two solutions for M, and one solution is already there 2.7, and what is the other solution? So, the other solution, let me see if I have it with me, though I do not have, but from here you get M subsonic, that solution. So, now you have Pc by P0 as a function of M subsonic. From isentropic relationship. So, from here you will get what is Pc. So, Pc is 780.5 kilopascal. So, the next part of the question, what is the design back pressure? That means what is PD? Same philosophy, AE by A star is a function of M. From here now you know what is M supersonic. In fact, you already know what is M supersonic, it is given as a part of this problem. So, this exercise is not necessary. So, M supersonic is 2.7. So, PD by P0 is a function of M supersonic. Right. So, from here you will get what is PD, that is 34.4 kilopascal. This is also isentropic relationship, because all these diagrams drawn here, these do not include any shock. Okay, so, you can use isentropic relationship. Next part, that is question number 5, is what is the back pressure for which normal shock will occur at the exit plane. Okay. So, if the normal shock occurs at the exit plane, then the design Mach number condition is obtained just before the exit plane, right. So, if you write A by A star as a function of Mach number 1, you can, so Mach number upstream of the shock, say u, it is clear that at the exit plane, if the shock is there, at the exit plane just before the shock, you will have this relationship hold true, because it is isentropic till just before the shock. So, till just before the shock you have this A as A E, A star is area at the throat and function of Mach number at the upstream, and in fact from this relationship only we calculated what is AE. So, this mu is 2.7. So, let us call this as m1. Now, once you know what is m at the upstream of the shock, you can calculate m at the downstream of the shock. So, by the formula between m2 and m1. So, m2 square is equal to m1 square plus 5 by 7 m1 square minus 1, this is with gamma equal to 1.4. So, from here you will get what is m2, I do not have the value, but you will get what is m2. So, this is m at downstream of the shock. So, you have P2 by P1 as a function of m1 and m2, this is the normal shock formula. Okay. So, if you have obtained P2 by P1, sorry, if you have obtained m1 and m2, you will get P2 by P1, and P2 by P1 is nothing but the shock which exists at the. So, in the previous class we mentioned that as the point what, point A, B, C, D, E, F, G, right, G point in the. So, I am trying to give a same symbol as the what we did in the theory class. So, okay. So, at this point G, so P2 by P1 is Pg by Pd, right. So, you know what is Pd already. So, from here you will know what is Pg. This is 286.5 kilopascal. Okay. So, this is question number 5. Question number 6, what is the range of pressure for which there is no shock inside the nozzle? When there is, what can you tell what is the range of pressure when there is shock inside the nozzle? So, that range is this one, for which there is shock inside the nozzle. What kind of shock? Normal shock inside the nozzle. Okay. So, what is the pressure for which there is no shock outside the inside the nozzle? That is P less than Pg. So, the answer to that, what is that question number? Question number 6 is Pb less than Pg will have no shock inside the nozzle. Okay. Yes, Pb less than Pg. So, for pressure less than G, all the shock will be outside the nozzle, right. So, no shock inside the nozzle means the question is there is some shock, but shock only outside the nozzle, that is the meaning of the question.
Even if it is greater than Pc also there is no shock.
No, even if it is, so when the question is asked no shock inside the nozzle, the question that is, I mean the question setter means that if there is a shock, that is outside the nozzle. These are trivial cases when there is no shock at all, question about, there is no question of inside or outside. So, you are very correct that for the region for P greater than Pc, there is also no shock inside the nozzle, but in that case there is no shock outside the nozzle also, there is absolutely no shock. So, when you say no shock inside the nozzle, that extra qualifier inside the nozzle tempts us to pinpoint this region where there is shock outside the nozzle or expansion wave outside the nozzle. Okay. Then the next question is question number 7. What is the range of back pressure for which there is oblique shock at the exit? So, if the pressure is between G to D, there is oblique shock at the exit. So, Pb between Pg to Pd, oblique shock at the exit. And finally, the last part of the question is what is the range of back pressure when there is expansion wave at the exit. So, when Pb is less than Pd, that is somewhere here, then there is expansion wave at the exit, oblique expansion wave at the exit. Okay. So, this problem is a very representative problem. By working out this problem, you will get a complete picture of what are the ranges of possibilities in a converging diverging nozzle. So, so far we have studied various aspects of one dimensional compressible flow with and without shock, and all these have been illustrated well through examples of converging and converging diverging nozzle. However, we have made two important assumptions for our calculations. One is the flow is adiabatic, and second the flow is reversible, because except for the location of the shock we have assumed isentropic flow. What happens if the flow deviates from isentropic flow? So, one possibility is that the flow still remains adiabatic, and that is not a very bad assumption because compressible flows are very rapid flows. So, adiabatic assumption may work well, but the flow is not reversible, and the lack of reversibility is because of friction in the flow. So, if we consider friction in the flow, what happens to the modeling, to the analysis of one dimensional compressible flows, that we will take up in the next lecture. Thank you.